Hello all, I am Suyash Bhagat from the Indian Institute of Technology Bombay, and today I'll be talking about the confidentiality of amounts in the Grin cryptocurrency. Grin cryptocurrency is a relatively new project which is backed by the Mimblewimble protocol. The Mimblewimble protocol is a blockchain protocol which relies on homomorphic commitment, and it provides scalability, privacy and fungibility all at once. This particular feature of providing all these features at once is something which seems to be very promising. Mimblewimble does not have any addresses or accounts, and even the amounts are hidden, and it hides the amounts using Pedersen commitments. Mimblewimble was first implemented by two projects, Grin and Beam. Now we'll talk about the outputs in Grin. So each output on the Grin blockchain is essentially a Pedersen commitment. And Pedersen commitments, as we know, are homomorphic, perfectly hiding, and computationally binding. So homomorphic means that, let's say I have Pedersen commitments P1 and P2, which commit to amounts A1 and A2 respectively. So if I compute the quantity P1 plus P2, then this new quantity becomes a Pedersen commitment to the amount A1 plus A2. Of course, Peterson commitments are also perfectly hiding, which means that given a Peterson commitment, even a computationally unbounded adversary cannot figure out what the amount it commits to. Further, it is computationally binding, which means that for a computationally bounded adversary, if he computes a Peterson commitment to a particular amount and publishes it, he later cannot change the amount what the Peterson commitment commits to. As far as Grin is concerned, in Grin amounts are 64-bit integers, non-negative integers, and we have a blinding factor k, which is a scalar, and the Pedersen commitment or the output is computed as k times g plus a times h, where the discrete log relation between g and h is assumed to be not known. And of course, this particular operation is done using the elliptic curve cryptography framework. And as we know, Pedersen commitments are perfectly hiding. Given an output P, it is infeasible to find what amount it commits to. And each output on the Grin blockchain comes with a range proof proving that it actually commits to an amount which is 64-bit and is non-negative. Now let's talk about a Grin block. So a Grin block has headers and it also has some transactions. So the header is characterized by a block height and a scalar quantity known as kernel offset, and we have some transactions. The first transaction in each Grin block is known as the Coinbase transaction, and there are the other transactions are known as regular transactions. So in the Coinbase transaction is basically used to pay the miners for mining the block, and it does not have any inputs. It has only one output which is owned by the miner, and this output is known as Coinbase output. And the regular transactions can have any number of inputs and number of outputs. However, this is not the representation we actually see on the Grin blockchain of blocks. The transactions in each Grin block are aggregated using a protocol known as Dandelion. So Dandelion basically helps in hiding the source of these inputs and outputs, and it also aggregates the transactions. So our final block would look just as a single transaction, which in which we might not know which amounts from the inputs are transferred to which particular outputs. One more thing we observe is that, let's say the output O3 is equal to input I5. This means that the output in regular generated in regular transaction 1 is spent in regular transaction 2 itself. So therefore we do not need to include either O3 or O5, since it would not affect the amount balance equation of the block. And this process is known as cut through. So after the cut through, our simplified block will just have 4 inputs and 4 outputs, out of which one is a Coinbase outputs, and this block is added to the blockchain. We will talk a little more about the Grin block and its validation. So continuing our previous example, the outputs other than the Coinbase output are known as regular transaction outputs, or RTOs as an abbreviation. Each block contains n kernels where n is the number of transactions. So we had three transactions for this block, one Coinbase transaction and two regular transactions. Therefore, we have three kernels. Each kernel contains fees, a kernel access, and along with that, a Schnorr signature which proves that each kernel access is of the form xi times g for some scalar xi. So we'll see what's the use of these kernel accesses. The Coinbase fee is always set to 0 and the constant mining reward is 60 Grin per block. And the block validation check looks something like this. So let's concentrate on left hand side. We have the sum of amounts, sum of outputs, sum of regular transaction outputs plus the sum of fees times h minus the inputs. So this check basically is to validate that no new amount is being created. So the sum of amounts in inputs must be equal to the sum of amounts in outputs plus the fees. So on the left hand side the coefficient of h would be 0. However, there would be some coefficient of the base g, and to balance that we have this right hand side. Other than this, the kernel access and the kernel offset times g term is used to ensure that in a transaction, if two people are involved, they do not get any information about each other's as blinding factors. Moving on. So the idea we are trying to explore here is that even though Pedersen commitments are perfectly hiding, can the transaction structure in Grin reveal any information about the amounts? So let's say we have three blocks at block heights h1, h2, h3, and of course they have some inputs and outputs and fees. So now let's say the Coinbase output in block h1 is spent in block h2. Therefore these two quantities are equal and therefore the amounts in them are also equal, which is equal to the constant mining reward plus the fees of block h1. And now this amount gets distributed to the regular transaction outputs in block h2. Therefore we would have the sum of amounts in these two outputs would be r plus fh1 minus fh2. We subtract the fees of block h2 because to pass through this transaction and to include this transaction in block h2 we need to pay some fees to the miner. Now we can establish an upper bound on the total amount present in each of these regular transaction outputs in block h2 because we already know the sum and we already know that the amounts in these are non-negative. Similarly, now let's say the Coinbase output in block h2 and one regular transaction output in block h2 was spent in block h3. So now we are trying to compute what's the sum of inputs in block h3. So the amount in this input is fairly clear, which is r plus fh2, and the amount in and the upper bound on this amount is similar to that of upper bound on this amount, this output, so which is r plus fh1 minus fh2, and if we add them we get the total amount in the inputs of block h3, which is 2r times 2 times r plus fh1, and this gets distributed in the regular transaction outputs in block h3, and therefore we can compute the upper bound on the amounts in the regular transaction outputs in block h3 as 2 times r plus fh1 minus fh3. If we just simplify this term on the right hand side, so the first term becomes the total block reward from block h1, second term becomes total block reward of block h2, and we subtract the fees in blocks h2 and h3. The reason for simplifying this is that we intend to design a general strategy to compute the total number of donor Coinbase outputs. So these two Coinbase outputs are donors for this particular block, in the sense that the amounts in the outputs of this block are coming from these two donor Coinbase outputs. To automate the process for computing such upper bounds for all the regular transaction outputs on the Grin blockchain, we model it as a directed graph where the nodes are defined as the blocks as well as the Coinbase outputs, and the edge set is defined as, now suppose a Coinbase output v1 from block v1 is spent in block v2, then we draw an edge between them, and if at least one regular transaction output from block v1 is spent in block v2, we connect v1 with v2. To just to continue our example, we had three blocks, so here we'll have six nodes because the blocks as well as the Coinbase outputs are modeled as nodes. So here we had the Coinbase output in block h1, which we define by green color, and the blocks as orange color is spent in block h2, and the Coinbase output in block h2 and one regular transaction output in block h2 is being spent in h3. To consider a real life example from the Grin blockchain, say we have block 1493. So the inputs of block 1493 are sourced in blocks 60, are essentially two Coinbase outputs from blocks 16 and 18, and one a regular transaction output from block 1489. Similarly, the outputs of this block are spent in blocks 1504 and 1514. Now we'll compute the flow upper bounds and formally define what a donor Coinbase output is. So a donor of a block B, we call a vertex C as a donor of a block B if there is a directed path from C to B in the graph as defined in the previous slide. So considering the example of a block 1499, let's say we trace the source of of its inputs, and we get four blocks. Now we continue to find the sources of each of these blocks until we find Coinbase outputs. So we go on and we stop whenever we have found all the reachable Coinbase outputs, which we call as donors for this particular block. So this particular subgraph, we call it as a flow subgraph for this block. Now, as we can see, the total amount flowing into this block is contributed by these 7 Coinbase outputs. Therefore, we can establish the upper bound on the regular transaction outputs in this particular block, and we can write it as, so the first term is 7 times r, which is because we have seven different donors, plus the fees in each of these donors, and we subtract the fees in all the orange blocks, as we know that we would need some fees for amounts to be transferred from each of these donors to the main block 1499. And one thing to note here is that there might be multiple directed paths from each Coinbase output to the main block. So for example, the Coinbase output in block 9 has two paths, first and the second, but we consider only one path as we want to avoid double counting. Now if we analyze this particular way of computing upper bounds for all the regular transaction outputs in 612,000 blocks, we now gauge the effectiveness of this particular upper bounds and try to interpret them by computing a quantity known as flow ratio of each RTO, where flow ratio is defined as the flow upper bound, which we computed using the graph based analysis, divided by the trivial upper bound. So a trivial upper bound for an RTO at block height h is essentially the total Grin supply until block height h. And now if we plot the flow ratio versus the block height, we get a plot something like this. So if this ratio is close to 1, it essentially tells us that the computed flow upper bound is very close to trivial upper bound, and it does not give us any non-trivial information about the amounts in these RTOs. And similarly, if it's close to 0, it says that the flow upper bound or the upper bound we have established on the amounts is quite small. So here we see that for most of the blocks, the flow upper bound is very close to 1. Flow ratio is very close to 1. For around 88% of the blocks have flow ratio greater than 0.9. However, there are these dots which have a flow ratio significantly smaller than 1, and 6.6% blocks with block height greater than 100,000 have a flow ratio less than zero point 0.5. So one more interesting thing we observe in this plot is that a jagged pattern in the flow ratio as we zoom in this part. So the jagged pattern is clearly not known. Uh, the 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 exact reasons behind this pattern is not known, although we estimate it to is to the we attribute it to the fact that the miners might be accumulating their mining rewards in a few outputs, because of which this steep slope is happening, and the slow decline is because of the naturally increasing trivial upper bound as block height increases. Now, the unspent RTOs depict the current state of the blockchain, and therefore we analyze the flow ratio for all of the unspent RTOs. And again, here we see that for most of the unspent RTOs, the flow ratio is very close to 1 from this histogram. Around 95% of the 110,000 URTOs we analyzed, the flow ratio was greater than zero point 0.9. However, there were 983 URTOs which had a very small flow ratio, very close to zero, and the upper bound was less than 1800 grins. So this 1800 grins is typically minted in just 30 minutes. So this is a very small amount, and therefore we found an upper bound on around 1000 URTOs, which was in a very small range. So our conclusion is that confidentiality of most of the URTOs is present using the graph based analysis we just described. However, there are a few RTOs in which for which the amounts could be found in a very narrow range. So as I had explained it earlier, the question we are trying to answer here is, can the transaction structure itself reveal some information about the amounts in spite of perfectly hiding commitments? So we expect this flow ratio to, for most of the URTOs, to be to push towards 1 as the transaction volume increases. So the currently the transaction volume is small, for Grin because of its less popularity. Further, linkability in inputs and outputs could be leveraged for tighter bounds. So if I know the relation between, or if I could disparately or find the distinction between transactions, then the upper bounds could be even tighter. And of course, since Monero and Beam also has Pedersen commitments, it would be interesting to design such analysis for both of them. In the last part, I'll be talking about the related work. So, as far as to the best of our knowledge, no work has tried to address the confidentiality of amounts of Pedersen commitments. However, there has been related work in traceability of inputs and outputs in Grin as well as in Monero. So Ivan Bogati has claimed to have traced 96% of all Grin transactions by listening to a lot of peer nodes. So the idea was that, so the stem phase and fluff phase are two parts of the Dandelion protocol, where stem phase ensures anonymity of the transaction, and fluff phase, it publishes that transaction to all the other peer nodes. So here, when the transaction reaches the fluff phase, it, since the super node is connected to many other peer nodes, it is also published to the super node, and therefore transaction aggregation is not possible in such scenario, and therefore linkability between inputs and outputs can be uh, can be computed. Another one is about the traceability in Monero, where Kumar et al. Showed some strong results. Their idea was that the 65% of the transactions on Monero as of Feb 2017 had had zero mix-ins, and because of such zero mix-ins, it led to a cascade effect, in the sense that if this transaction has a zero mix-in, we know that this address is spent. So if this address is used as a cover address in some future transaction, then we definitely know that the remaining address is the one which is spent, and so on. Another idea was a more intuitive one, in which they said that for in a given ring, an input is spent, that input is being spent which is the most recent on the blockchain. A concurrent work was presented by Moser et al. About the traceability of the Monero's blockchain, and they proposed a novel bin sampling strategy as a countermeasure for the two flaws we just presented. In this, the idea again was simple, that they proposed to have small bins of addresses which are at the same height or neighboring heights, and this kind of a structure would uh, ensure that the linkability information cannot be established between inputs and outputs. And they also characterized Monero usage behavior, uh, and proposed this bin sampling model based on the user behavior. Lastly, I'm adding some references if anyone wants to dig in further, and I would be happy to answer any questions if anyone has.